Okay, 5 p.m. We're back in the plenary after the excursion to KSAT and the airport. So for the next almost 2 hours, it's the plenary on sensor synergy. Go ahead, Johnny.
Very good.
Floor is yours.
Thanks, Eero, and welcome back, everyone. So the Synergy gang is Van Holt, Bertrand Champron, Dr. Fab, myself, and Lucille, and with contribution then from a broad range of other people. And we are not afraid of receiving more input from additional contributors when it comes to the white paper. Of course, the sensor synergy is the most important aspect of the proceedings, and it will be the best white paper. So you better make sure that you have an authorship into this. So hopefully the presentation shall trigger you to sort of consider that next step of yours. So we follow the structure of, in the beginning, finding the objectives, then looking at some of the innovative new findings, achievements, and then again go after the gaps and the deficiencies and look for the future, the bigger picture. But what we mean with sensor synergy now is perhaps important to remind you all about. You may have a clear understanding of it already, but it is simply going after the frontal structures in any kind of imaging, satellite imaging system. So frontal structures are typically found in sea surface temperature field, in ocean color distribution and concentration, in altimeter-based sea surface anomalies or sea surface height anomalies, SeaSAR-based surface roughness. And just to remind you that for the SeaSAR-based surface roughness, the front boundaries there are typically induced by presence of current fronts, presence of waves that interact with current fronts, and presence of wind in frontal boundaries and surfactant material in frontal boundaries. Scatterometry largely is also a surface roughness detector machine, but it doesn't have the resolution. But still, there are fronts also in the SCAT detected surface roughness, predominantly connected with winds. Then we have the SeaSAR-based range Doppler shift, which also must be taken into account. Visible derived sun glitter. And last but not least, also in the marginal ice zone, we do have sea ice ocean boundaries and frontal structures as well. So maybe we should start with the latest. This is a combo of the SAR image and Sentinel-3 image from yesterday. And we see clearly the presence of where we are. And you see the cloud streaks in the optical data. And you see how nice under northerly winds, the optical image is a beautiful detector of sea ice fields because there are practically no clouds over the sea ice as it is cold and dry coming off the ice edge. So you see spectacular details in the marginal ice zone. Look here. And then you have it in the SAR image at the comparable structure, although this is not overlaid. And we see these nice structures up along the coast of Spitsbergen. And as it happened to be nice weather coming up here a few days ago, we also looked at this visible image again, and we made an animation of it. There are, in fact, more than 12 passages of this area in course of a 30 hours period. So it's a huge temporal frequency that we are now able to take benefit of, provided, of course, that it's cloud-free. And here you can see a little bit of an animation. And the last image you now see where the cloud visible image has now been taken into account the thermal the thermal image as well. So you see now effectively the brightness temperature at the emitting top of the clouds. And pay attention to these guys that you see around here, because on this day, 1st of May, we flew this red line with SAS, and I was happening to have a window seat, and I saw this. So they are exactly correlated with these two guys. You see particularly this one here quite easily. And also the one up there. It's not so good in this image, but it's good if you sit in front of the screen and look at it. And they are present there. Of course, not surprisingly, it should be present there. It's just happened to be an opportunity. So satellite sensor synergy, the strength and the goals of this approach is that the mesoscale structure of the ocean surface at synoptic scale at a resolution of 100 to a few kilometers reveal this mixture of oceanic and atmospheric signatures and associated processes. And it roams around everything from waves to wind, internal waves, wind streaks, hurricanes, polar lows, filaments, upwelling, meandering fronts, spiraling eddies, convergence, surfactants, oil spill, and sea ice. And these features and these underlying processes are expressed through a broad range of imaging mechanisms. And we happen to be able to document that from playing this sensor synergy approach. Some of these structures that we've seen are almost impossible to detect from in situ observations at the surface. So we are challenged here because of the validation is extremely difficult. It's also challenging in a way that it's not just fun to observe these processes and structures. They are beautiful, but do we understand the underlying quantitative process properly? How does these processes influence the pathway of energy, fluxes, 3D motions in the upper ocean, 3D motions in the atmospheric boundary layer, physical biological interactions, and also how they concentrate and move around floating material. But it seems, and hopefully you take the message, you already probably have a good view of sensor synergy and you believe in it. I think it is the way to go about this. It does have a couple of very attractive advantages. First of all, from the fact that each imaging mechanism do have a kind of inherent limitation. By doing the synergy, you may in fact remove those limitations that each of the sensors have individually. You shortcut those by finding the combinations around these inherent individual limitations. And it does provide out of that a significant improvement in space-time coverage, for sure. And it's clear that if we did have today precise arrangement of sensor synergy studies in given supersites, or what we call natural laboratories, these would become excellent platform for waiting for the new launches of satellite. Come on, let us validate you in our favorite supersite. So this is a bit of the seed into this whole thing. Now let me show you a bit of something that was done over some years and culminated with a paper by Vladimir Kudryavtsev in 2012. And to our surprise, we find that this paper is very poorly cited. And it's a sad story. But therefore, I take the opportunity to remind us about this concept of sensor synergy, in which the SeaSAR instrument is the core, sort of the mother sensors, and all the others are coming in to sort of fill in the limitations of the SeaSAR, which of course is there as well. But the SeaSAR detects a normalized radar cross-section. That is connected with the surface roughness. The surface roughness is a combo of short Bragg waves and the waves at the intermediate scale, 1 to 10 meter, but also in presence of longer waves of 100 meters and beyond, towards the swell field. So this is what the SeaSAR is primarily aimed to detect, the surface roughness due to these combinations of different wave fields. The wave also breaks, and that creates a new kind of opportunity to trigger a new setup of Bragg waves. So in the same time, it's registered in the normalized radar cross-section. Then we have mesoscale currents out there, and the mesoscale currents are connected with gradients. And some of the most dominant mesoscale currents that we all love to study are mesoscale eddies. But they consider it as mesoscale currents now with their gradients. These gradients are connected with sea surface temperature fronts. And at the same time, a sea surface temperature front is talking to the atmospheric boundary layer and triggers changes in the local wind. This is changing situations in the boundary layer from stable via neutral to unstable stratification. Immediately, the surface roughness will then go about this and change its signature. Then we have these interactions between mesoscale currents and surface roughness patterns that in turn leads to new surface roughness patterns. And this is wave current refraction, essentially. Then popped up the Doppler method many years ago, although it was already suggested to be potentially a feature that should be explored by SeaSAR already in the 70s. And I think Bob Schuckman in the audience was one of the first one who pointed to this possible opportunity. But the amount of data at that time were not enough to sort of go into that. But now we can do the mesoscale current gradients via the Doppler and also start to pick out that surface current as was presented in the Doppler shift presentations earlier today. So this scheme here has been there since 2012, and I'm afraid that it's disappointing to see how few people who bothers. The DOPRIM is there as a reminder, because all of what you've seen in this scheme is also possible to simulate with DOPRIM. So we do have here a play tool that we can tune all of these different quantities inside that flow chart and do it in the DOPRIM and see what the impact of that is on the normalized radar cross-section as well as on the Doppler shift. And we would not have been able to do this without the excellent work of Vladimir Kudryavtsev, who unfortunately is not here for an obvious reason these days. Synergetic approach to the upper ocean dynamics through this concept now is that we have mean dynamic topography, and we have mean dynamic topography plus sea level anomaly. For the ocean, that is an essential background constraint on the large scale, 50 to 100 kilometer scale kind of dynamics in the ocean. Then we have the SST field with its gradients. We have the ocean color with its gradients. We have the cross-section with its gradient, and we have the Doppler. And we have also the mean square slope and its kind of variability, which also triggers into the sun glitter. We have sea surface salinity and gradients, and we have wind stress and wind stress gradients. And out of this, if we can sort of arrange this into a data-driven, physically constrained approach, we can look into this from the fact that can we produce the total surface, the total current, the U mean plus the U perturbing, the divergence of the current field, the curl of the current field. These are the two drivers for all the fronts we see in most of the SeaSAR images. And then we have the opportunity to go via wind speed to Ekman current and start to see the estimate of that, plus the near inertial oscillation. And does this allow us then to look into the ocean upper layer, the mixed layer? If we have a 2-layer model or something like that, we may play with this and indeed do that. And I think what Clément Ubelmann is doing with his backward-forward nudging BFN model is probably where the next step will be visible, where he has a 1.5-layer QG model that can easily be used with all these quantities that he has ably estimated inside his BNF BFN, and then take out the mixed layer depth variations to it. So the tools are there, and it is time to start to now devote this effort to collect this sensor synergy and start to go from 2D surface expressions into 3D upper ocean dynamics. And combination with models will be essential. So the numerical ocean modeling community now must be taking part in this exercise with us. It's not meant to demonstrate that the models are poor. It is just meant to be saying that we have what we have, and that model can learn from that. You have a model, we can learn from that. And we have some examples of where this has been successfully done already. And I think the sea ice modeling at the Nansen Center with NextSim and the sea ice drift and damage estimation from Sentinel-1 SAR that Anton presented earlier today is such an example that we could take further into upper ocean modeling and upper ocean dynamics as well. So, okay, the mean dynamic topography, synthetic aperture radar, what has that to do with that? Well, we can do the mean Doppler over a long period of time. And when you do that, you basically now constrain the variability and its signal, and you just refine over and over again the mean contribution to the Doppler. And that is not more than what you could say could be connected to the mean dynamic topography. This is an example of this, and it has a resolution which is much better than what you get from the gravity mission, from GOES, and the geoid estimation of that mission. So it can fill in and be allowing us to go from a sort of 100-kilometer resolution gradually towards finer than 50-kilometer resolutions in mean dynamic topography. Then we have that in place. Then we can look at the brightness temperature for Moody's in the left and just overlay or compare to the surface roughness from Envisat. The vector in the Envisat image is a wind field product. But here you see immediately a couple of things that our eye catches and where there is commonality. It's this guy, this anti-clockwise eddy here, and it's this clockwise eddy here and there. And then it's a very strong signal of that frontal boundary that sort of winds upwards. The two images are about 2 hours or something like that apart, I think. And or is it just 30 minutes? 2 hours, yeah. But what can we do with this? If you look at the sea surface temperature field, we can do that immediately into a proxy for a QG-derived vorticity field. This is the QG-derived vorticity field. And when you look at this now, you are immediately now illustrating areas of dominating convergence, areas of dominating divergence. We in the SAR field, we always find out that where there's a bright front in the SAR image, it is due to convergence. So here you see in the red color, it is now I have to be reminding myself what's the scale here. It's negative in blue. So negative in blue means convergence, I think. So you see that the structure here is not just converging. It's both place in most of the places, both converging, diverging dynamics corresponding to the sea surface temperature field and its proxy in a quasi-geostrophic model estimation. And the correlation to the surface roughness in the SAR is quite impressive. And it's also showed this other front that sort of migrates upward. So dynamically, this can be done, and we have the quantification of the converging field produced and allow us to compare to the SAR image. So The synergy takes us further because this same feature, in fact, was also discovered in ocean color in the upper right and in the sun glint in the lower left. The paper that published all of this was the 212 paper by Vladimir Kudryavtsev. It is very tempting to look at these SAR images like this one to the left. I think this is, in fact, even an ERS-1 SAR image. And then to look at all this spiraling structure and the formation of these eddies and so on and so forth, and start to think upper ocean. What is the connectivity between that surface expression in the SAR image and the upper ocean structure? This is a new thing that I've not seen very often before. I don't think I've ever seen it before. This is a North Atlantic model, 1/60th of a degree resolution, meaning 2 kilometers. It is done by the group in Grenoble by Boudon and Le Sommer. You see Iceland up in the middle up there, and you have the Orkney Island, Scotland here, and the Faroes up there. What do you think you see here? You are seeing mixed layer depth. Mixed layer depth. The dark is deep, the light is shallow. And it shapes up like mesoscale structures in the mixed layer depth, meaning that there has to be a significant amount of vertical motion to sort of shape up this structure. This can not only be done purely by advective motion, a horizontal advective motion. This must be connected to 3D dynamics and importance of vertical motion. So we looked into the SYN tool, same area, but not exactly the same. But what you see here is sea surface temperature. And you have the Scotland and Orkney Islands up there. And what you see here in this pattern here are shapes that is corresponding in magnitude, in size, and in orientation and complexity. Here, the dark is deep, the light is shallow. But you see these filaments that creates this sudden mixture between light and dark color SST, meaning that here there is a temperature gradient that could potentially be connected with a variation in also the layer thickness. And this is the equivalent ocean color image. These are both satellite data from Sentinel-3. And again, you see these structures that is all over the place, where there are light, high concentration chlorophyll into the reddish, and dark green, low concentration chlorophyll. And it's not that particularly sort of, doesn't take too much of your imagination to look at this and then look back at this one here and see that at least your eyes wants to tell you that there's something of common here. There's some commonality in the structure, but it's absolutely two completely different things we are looking at, mixed layer depth and ocean color or sea surface temperature. But the suggestion for some kind of a correlation is there. To be able to examine these things in a systematic, efficient, and let's say stimulating way, the use of these SYN tool platforms that Ocean Data Lab has generated is just super valuable. So I can't give enough credit to Dr. Fab for what they have come up with and the way they are developing this further. So we are helping out a little bit, and we will try to do an Arctic portal of this SYN tool in polar stereographic representation. What you see here is a little bit of example of that. You see a model field with sea surface temperature. It's 2 paths which assimilate satellite data and in situ data. And you see the cold water in the Arctic, and you see the the warmer water as you progress towards the south and the inflow of the North Atlantic water from the Gulf Stream. It's a day in April 17th, 2023. Then we have the surface current from this model on top of that. And we have the sea ice model on top of that, the next sim sea ice model. And now I want to check how good the SeaSAR is. These guys has not used SeaSAR at all. So can I use this? Can I use this to train my SeaSAR analysis? Or can I use my SeaSAR data to improve the simulations? That's what it's all about. And I think Anton did demonstrate quite well some of this in his presentation. We can also look at these ocean color data. Sometimes it's in fact clear water also off the coast of northern Norway. So here you are with the Lofoten island is here, islands. And this is ocean color on the 21 June 2020. And look again at this color concentration and distribution. And keep in mind that there is something here that potentially is also connected to the mixed layer depth. And also look at these different shapes here. There's an enormous amount of interesting structures. That one is a clockwise rotating eddy. This one there, I'm not tall enough to reach up with. That's an eddy vortex, but there is a anti-clockwise rotating eddy. That is red, full of chlorophyll. The clockwise rotating, the cyclonic rotating eddy is very limited in the amount of chlorophyll. So one is connected with deep water, the other one with shallow water. If this is the case, then I could go through all of these circular structures and say that, but then I fail because this green guy up there, that's also a anticyclonic eddy, and that should have been filled with chlorophyll, but it's not. And the reason why it's not is because it has probably burnt out all the chlorophyll. It's an old one, whereas this one in the red-rich one is a young one. So there's a temporal information in these surface signals that we have to cope with, because the chlorophyll is in fact having this kind of a daily to sub-daily variability to it. The SeaSAR image on top of this gradually starts to sort of show that indeed we see this very strong anticyclonic eddy that was red in the ocean color. It's seen in the SeaSAR image, and it's low backscatter in the center. It's not good, but it's you see it there. There's a lot of other low backscatter structure also in there, but this low backscatter center is suggested to be connected with the rich amount of chlorophyll there that could potentially have a surfactant effect on the surface, damping out the small-scale roughness. And if we take this one step further, we go into a very detailed structure. This is ocean color to the left. It's a SeaSAR image in the center, and it's Sentinel-2, red, green, blue in the right. And there are clearly features that are talking to each other. And one of the challenges in this SeaSAR image is that what kind of frontal structure do we see? Where do they come from? And here you see a bright front, and you see these filaments of low backscatter fronts. But looking at the ocean color data, there is potentially a possibility here to claim that this one is a converging front, whereas this one is due to filaments of high concentration of chlorophyll, which this chlorophyll signal wants to tell us. And it's not a surprise that we've seen this before, but it's always hard to say, well, it could be a diverging front, It could be water that separates, and suddenly that creates an area with very low surface roughness because the wind hasn't been able to sort of take full act on it yet. But these things are the challenges that we need to continue to explore from this synergy point of view. SST field, to the left here, very little gradients at all in this, in fact. So, but there are structures that stands out that basically are talking to each other. Whereas in this case, the absolute dynamic topography doesn't have the resolution. This is just an area of 30 by 30 kilometer or thereabout. So it doesn't at all help us in this case. So that's part of the first story of the synergy. And I now give the floor to Ben. And sequentially now it will be Ben, and then it will be Fab, and it will be me, and it will be Fab, and it will be Fab, and it will be me.
Check, 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 check. So I'll show you more in my longer talk, but we started looking at these images in the Western Pacific, and they were really related to this archaeological project we have on the island in the Micronesia. We were supposed to fly airborne LiDAR to look for more archaeological features and then understand the ocean around it. And then COVID hit, so I started wandering into looking around, what else can I do? So I ended up with this, finding this extensive collection of ALOS-1 SAR imagery, of course, which is L-band in the Western Pacific. And it showed a lot of these convergent fronts, not a lot, but quite a few. And so we started putting those together with different types of imagery, different types of products, including what was horribly named JPL Kodak product called MER, but it's a blended SST, interpolated SST made composited from many different sensors with a background data is radiometer, so it can be coarse resolution, but it is a cloud-free 1 kilometer pixel data set on a daily basis. And then Oscar currents, which are derived from multi-sensors, also a Kodak product, which I think is like a 5-day average. It's kind of a running window, a 5-day average. And then we started adding another Kodak product called the CCMP, which is a blended sort of a composite wind data to try to understand what we were seeing. So here's my first example. One of my favorites is this front. So the other thing is I purposely didn't look at the Kuroshio along the western boundary. I sort of started looking elsewhere because I figured that, you know, these major currents, people know that we all know that there's convergent zones. Yanni showed them, and they've been seen for 40 years since SeaSAR over the Gulf Stream and so on in a smaller region. So, but this one is kind of away. And then here's one segment of a 3-panel segment, just to show some higher resolution with a little island there. And then we have overlaid these multiple data sets together to see what's going on. And the wind data are the red or orange vectors, and the current data is the black vectors. And then we basically made we drew these lines, the convergent fronts, when we just drew a line, followed that front as a line. So we wouldn't be looking at the SAR data. We just find these convergent lines, including the dark filaments too. So anyway, basically the converging lines, these convergent fronts fall right along this this large filament. And as I started looking at more and more of these, I realized that with adding this wind direction, usually these fronts are the winds and currents are in mostly orthogonal directions. So they're kind of there is a convergent front, and the fronts lay along this temperature boundary, this SST boundary. And maybe that's what's supposed to happen. But if the winds and currents are parallel, because you have a different situation. Here's another example. And a lot of the flow patterns of the currents there seems to be also some interaction with bathymetry. In this case, these islands that are poking up in the Western Pacific. In the next longer presentation, I'll show that this image actually, another scene was taken 3 days later, and there's some similarity between the fronts, but the winds are a little lighter. So, and it may be that the converging lines are moving toward away from the bright feature toward a darker feature. Anyway, it turned out that for 4 years, there was this crazy collection of ALOS-1 images, and my visual machine learning, I looked at these browse images and then I saw something that looked good on the ASF webpage, and I downloaded it. So, so most of the features that we've seen are related actually to the coverage as much as anything. But it turns out to be in a subtropical countercurrent area that, as discussed in this paper that I'll illustrate tomorrow, I guess tomorrow. Anyway, so there's also another nice time series of sentinel data over this main island that we're focused on called Pohnpei, which is the capital, is the capital city, the capital island, the main island of the Federated States of Micronesia. And you can't see it, but the World Heritage site of interest is down in the lower right corner. And we're doing the same thing with trying to understand these nice features. Did I skip one? And there's also showing convergent. There's a convergent line on the western side of the island that extends down. That's kind of weak. And there's also these little bright vortices that seem to be associated with the tidal flow. They're related to the coral reef inlets, and probably related to some sort of tidal flow. So we're looking at those images as well. Okay, so where we see these bright convergent cells, they seem to be, again, with these opposing wind and current directions. My hope is that we are able to quantify the SAR patterns based on the strength and the counter forcing of the winds and currents, so that the brightness of the convergent front is somehow related to these to the gradients and the winds and currents, as well as the temperature field. So Without these, I will say that I looked at every other sensor I could. I didn't look at ENVSAT, I have to admit, for coverage of this part of the world, and it was extremely limited. So that's why this seems so interesting. The fronts are away from the strong boundary currents, kind of in the middle of the ocean, in the middle of nowhere. And and the island sequence with Sentinel-1 is really interesting for various reasons, which I'll show in a longer talk. Okay. So, well, go off. Who's ever next? Come on up. But I'll go off the cuff. So I always thought L-band data was a little bit better for looking at ocean currents. So anyway, than C-band, because the C-band's so sensitive to wind, but that's another topic, I guess.
Yes. No, there will be some presentation also on different frequency synergy later. So yeah, this is something prepared by José da Silva from University of Porto. He's very interested in internal solitary waves, and recently there was a study in tropical Pacific, in this cold tongue, so-called. And so there have been some analysis of a lot of Sentinel-3 and Sentinel-1 image over this area to detect the internal waves, and also to look at the synergy with satellite, with altimeters from like SAR altimeters like Sentinel-3 or Sentinel-6. So that he has been analyzing quite a lot of SAR images and optical data. And then, so these are the results of his detection. So you see all the lines have been detected, which have different colors or different line type. They have been observed at different days. And on the back, what you see is a SST so this is a multi-mission blended SST product, but basically what you see is the tropical wave instability, the Rossby wave at the equator that are very large and very they are propagating also to the west, and they are you see them in the low resolution SST because they are huge, but we can see that they create very sharp front at the boundary, and also a lot of internal waves observed at the surface in this tropical wave. So there was one observation on the wave mode from Sentinel-1, so which is quite lucky because it's only one imaget every 100 kilometers along track. So and this happened to be just across one of these tropical instability front. And so we have on the left on the middle the small image mode from Sentinel-1 and wave mode, and on the left it's sun glitter image from Sentinel-3 Olshi, and the right SST from SLSTR on Sentinel-3. And so we can see on the upper part the internal wave packet on the sun glitter, and we see since Sentinel-3 has also an altimeter, we see also on the altimeter the cross section from the altimeter, which is an estimation of the mean square slope. You see some oscillation when you have this at the moment of the internal wave packet passing. And you see also that there is a standard deviation of the sea level anomaly that is increasing with an amplitude of 3 centimeters. So in fact, it's possible to detect the internal waves that you see on SAR and optical, also on altimetry, both on the cross section and the sea level. So of course, what is asking for is some more dedicated experiment in a wide swath mode over these tropical wave instabilities, and to organize some kind of to create some kind of a reference data set of these measurements over this tropical Pacific area, and the same with new missions like SeaSAR or Harmony. And so yes, so this is to put it in a wider context. So this long-crested internal wave are generally quite long-lived, and they are originating from the thermal instability, the tropical instability wave in the cold tongue of the Pacific. So this is something that that also is quite interesting to study, because it has some long-term impact on the air-sea interactions, and to understand also the climate variability. And this process, they include a strong dissipation rate. So we see that at the boundary of this instability wave, you see a very strong backscatter on the SAR. So this is caused by very intense breaking wave, even in low wind condition. So yeah, basically the idea would be to try to reproduce what has been done in a more controlled experiment with wide swath images from Sentinel-1. So this is something to the Sentinel-1 mission planning to help organize this experiment. So I give the floor to Yoni for this polar law.
Thank you, Fab. And while I'm rigging myself up, I think Jose is quite shy in claiming the importance of this work. Internal waves cannot be considered in isolation of climate change. Internal waves is one of the mechanisms by which heat and potentially also gas is transferred from the upper layer to the deeper layers. And internal waves are, in my opinion, very poorly treated in numerical ocean models. So that is, of course, partly because of the spatial resolution here. You need to have in order to resolve internal waves, you need to be at better than a kilometer in spatial resolution to resolve them properly. So there is, of course, a challenge in this. So then we go on to another example of synergy, which in fact was addressed also yesterday to some extent in terms of extreme winds. And Biao and Will, they show in this case how the SAR can be used in synergy with other radiometer observations for detecting polar lows. And the whole issue here is that these guys are fairly short in spatial scale, 200 kilometers or thereabout, and they are very difficult to observe with traditional in situ observing systems. And they usually, therefore, is not properly resolved in the numerical weather forecasting systems. Satellite remote sensing do have this capacity to detect these guys and also to track them. And we saw beautiful examples of that with the tropical cyclones in the Indian Ocean yesterday. And we know that this is possible to do. Commonly, it's been often mostly detected in the past through visible or thermal infrared imagery. Just lately, we've seen that the SAR becomes a key possible contributors to this, and not at least from the fact that whereas the thermal imagery cannot be used to estimate the wind speed, the SeaSAR can do that. And Biao and Will have in fact developed an automatic procedure for detecting these guys and to track polar lows in combination with passive microwave radiometer. And that's quite an interesting comparison he's providing here. So this is a scheme where they have the original image, they do the reprocessing and the reconstruction, and they use some kind of segmentation methods. And out of that, they are able to properly identify the center of the polar low. And this is necessary in order to start the tracking properly. So I'm not an expert by far on this watershed segmentation method. So if you ask me a question about this, I will just have to forward it to Biao and Will. But these kind of examples we've seen before. And it's a cross-section to the left, and it is the inversion to the wind speed to the right. And it's clear that in order to rely on the wind speed, one probably has to have a good handle on the wind direction. And some of the properties in the SeaSAR image is in fact giving us a signal of the wind direction, where you can see some of the wind streaks in the western part of this image. And that can be used to impose the wind direction. The wind speed in these polar lows are not necessarily of the highest that you are sort of associated with extreme winds. They can be 18 to 20 plus meters per second. But they are very small, and they are really, really dangerous for the for mariners, particularly fishing fleet in the Norwegian, Greenland, Barents Sea, are not happy with these guys if they can come unpredicted, because if they are out trawling, and they cannot turn the boat that effectively into sudden change in wind direction and wave direction. And this has led to a lot of difficulties in the past due to these polar lows. This is a nice one here now, synergy with passive microwave radiometry. What we see here is a water vapor. And it shapes up again nicely with the kind of shape we've seen in the SeaSAR image. And I would want to send a question to Ed Stoffelen, and it's basically partly invoked or stimulated by the comment from Ralph yesterday. What is this doing for the atmospheric boundary layer, and how will this effectively make something of a wind speed estimation a bit questionable? And Ed, are you there or are you not? If not, we could use the chat and send him a question from this auditorium.
Johnny.
Okay, that's good.
So, of course, in nowcasting, we train meteorologists always to combine RGBs, which also are a signature of water vapor content, and winds, because it's very important to them to understand the structure of the scheme. If we use, you asked for the effect. So the effect of moisture on validation is that it is part of atmospheric stability.
Yeah.
So when we have to translate buoy winds or model winds to stress equivalent winds, then moisture is part of the equation. And I mentioned yesterday that we have a problem with this in the tropics because moisture convection is not well resolved in the model, which also means that the moisture structures, of course, are not well resolved because they depend on these convective cells. And if they're not there in the model, that means that also the moisture distribution is not well captured. And but there we see most of the noise in the model correction for atmospheric stability and mass density, and what we need for the stress equivalent wind computation. Because if we go to buoys, then we are not suffering from this because it has if it has good moisture and pressure measurements, then we can do the correction. But then, of course, the moist convection causes a lot of wind variability. So then we have to integrate the stress equivalent wind over a certain time to be compatible with the 25-kilometer footprint of the spectrometer. So that's also causing some uncertainty in the topics. For the polar region, I've not seen this. So the moisture contents, of course, are much lower in the polar region than in the tropic. So I think it's mainly a tropical problem.
Well, I think, thank you, Ed. That was good that you could reply to this on the fly. And I think also that the Russians are working a lot on passive microwaves to detect the moisture or water vapor conditions in polar lows. So there is more than this example, that this is in case also in the high latitude regions connected with polar lows. The classical way that this has been seen in the past, of course, is through the thermal infrared and visible imageries. So where you see the cloud structure and how the structure and the pattern in the clouds are again lining up in a clear indication of the prime wind spiraling wind direction associated with the polar low. And again, you see the shape here. That is the shape that you find in the water vapor, of course, needs to talk to the shape that you have in the cloud structure, because that's where you do have the water vapor anomalies. So it's clearly an evidence of this kind of correlation there as well. And in this combination of SeaSAR and thermal infrared and passive microwave data, Biao and Will illustrate now that they can find the precise center of the polar low and then start to track it with very high precision, which is exactly the point that the users of this kind of information who are out at sea fishing or even also oil and gas industry on platforms may want to have such information with that particular kind of details. So that's the message from Biao and Will, and we proceed with a very interesting question. Can we retrieve sea surface salinity with polarimetric SeaSAR? And that's you.
Yeah.
Good.
Can I have the mic?
Yes, you can.
I don't look loud enough. Thanks. Okay. Hi, everyone. Okay. It's not very comfortable. Okay, so I am Thibaut Trayad. I'm a research fellow at the European Space Agency in Frascati. And I work on SAR-related activities, and mostly my research topic is on the secondary objective of biomass mission. So I work in the team of Diego. I guess you know more or less Diego Fernandez, and I'm in the division of Yves Louis Desnos. So today it's nice because I realized that in the MAG there was no oceanographer in the MAG of biomass. So it's good that I will be the voice of biomass for you, and I want to take recommendation, and we can talk about sites that are interesting to monitor, put in situ, all these kind of things I would like to discuss with you. So very fast, because I think I will present in the breakout session. So can we retrieve sea surface salinity with polarimetric SAR? So it's why we want to do that, because we are going to high resolution. So especially we want to have understanding in coastal areas. And let's say the two main constraints that we have now with a sensor that measures salinity is the resolution. That is 30 to 50 kilometers, that is not applicable in coastal areas. And also the fact that the land is warm, is hot, and you have a buffer of several hundred meters where you cannot have salinity around the coast. So there was a work actually made 20 years ago by a team that was kind of promising, and I was wondering why there was no more work on that. So I think with the coming mission biomass, it's nice to revive the activities and discuss about it. So I think this is the most important slide. I don't know if there is the. Yeah. So on the left part, you have the real part of the dielectric permittivity as a function of frequency and salinity. So low shade is freshwater, and then dark shade you increase the salinity. So you see that the real part is not much varying. It has a kind of homogeneous behavior with the frequency. But the imaginary part, it's where it's very interesting, because you see that at C-band you have very small variation, so 5 gigahertz. At L-band you start to have higher variation, and then at P-band you have a very good sensitivity. And also it's nice because you can realize that you reach a minimum. So it's like your imaginary part is 0, and theoretically you penetrate in freshwater. It's also interesting things, and biomass will maybe help us to have more understanding in this kind of behavior. So the main idea of the work is to understand, to have order of magnitude of the impact on the roughness and the dielectric properties of the water with these frequencies. Yes. So just very fast, I will go, because after I will, it will be more detailed. But here is the let's say when you look, the first observable that you can look when you want to understand what are the sensitivities, you can look at the Fresnel coefficient. And here I show on the left, so at C-band, so for the VV polarization with salinity, you see that at the Brewster angle, you have some variability, but we observe more. I don't know if you see my, no, you don't see it. Yes. So at the Brewster angle, you see a lot of variability with some variability with salinity, but when you are actually what we see, it's a mix of all this between 20 and 40. But at P-band, so you start to see a nice variation, and especially several dBs when you are next to the Brewster angle. So then if you want to have a good estimation, you look at, let's say, more realistic model on observable for example, normalized radar cross-section, or even some polarimetric parameters like copolarized phase difference. So I looked at these things. So here, just very fast, so the lines are 2 winds conditions, so 5 meters per second and 15 meters per second. And the column are the frequencies. So basically, you see when you decrease the frequency, you increase your sensitivity to salinity. And then the other interesting thing is the difference with 2 wind condition. So if you take at C-band, wait, sorry. So at C-band here, you have 10 dB difference between 2 wind conditions, between 5 meter and 15 meter per second. At L-band, so you decrease this sensitivity to roughness, and at P-band, you start to have the same level of sensitivity from dielectric properties and the wind contribution. Okay, so it's very nice, it's interesting, but you see that it's still close to, let's say, the SAR detection capabilities. It's some dBs. So you need to first understand all the contributors in this game, especially in coastal area where it's very complicated. But I think the biomass mission will be interesting for this kind of experiment. So tomorrow I will show more, let's say, where are the acquisitions that we may have in coastal areas. Yeah, so then mostly I want to have input from you guys for what we could do at P-band for oceanography. For example, with Fab, we were discussing about the Doppler at P-band, so that could be interesting to see. And so there is a lot of, I think, things to discuss.
Just to say that in biomass, there are definitions that have already been provided to the ground segment for acquisitions in the north and in the south, where we can do some best practice acquisition.
Okay.
I won't really present that tomorrow in the future missions, but what's clear is what we need from this group here is a clear recommendation that some acquisitions of P-band over the ocean and the ice shall be made. So if we can get that into the meeting notes, that would be really useful.
Yes.
Because we can expect a lot of nice things, right? It's a long wavelength, 70 centimeters. It'll be interesting. So if we can get that written down, then that would be helpful.
Yeah, and just to remind that it will be the first P-band ever in space and the first full polarimetric mission of ESA. So this is two major things, and we will have very interesting data sets. So for the acquisition plan, it will be more like a, let's say, proof of concept or specific experiment. Don't expect to have high revisit time. It will be like patch. I can explain it if you want later. Yeah, exactly. Yeah. Okay, I think that's it.
You say that we could do it more in the future mission.
Yeah, so it's been decided by Dr. Fab that this presentation here is better done in the future mission presentation tomorrow, and Craig and the co-chairs has agreed. So you can just see the slides, but there will be no comments to them. It's these slides here. So this just trigger your interest for the future mission session tomorrow. And here you may see a future mission concept proposed tomorrow. So we come to the first set of the conclusion now for this set of presentations before we start with the question and some in addition. And these are just a list of points that may far be the total and may also be, in fact, improved in terms of what it meant to mean and specify. But I think the ability to continue to start to continue to come up with a framework from 2D to 3D upper ocean estimation based on surface two-dimensional structures is something that is worth exploring in chlorophyll, SST, roughness, mixed layer depth, and also in combination with model. And this framework is nothing more than, it's been said many times and it's been applied in different ways. It's done today in not necessarily for satellite data, but in some ways it's clearly done by ocean numerical models. So it is the level of data that is out there available for us. It's low resolution data, it's a high resolution data. And it is to come up with a dynamical framework for how to use these data sets constrained by physical methods. And gradually establish an opportunity to come up with some new parameter estimation and to have those in a way available for model validation and for two-ways exploration. What is a model? What can the model do here, and what can can the satellite do, and how can we combine to improve? And the synthetic aperture radar will be a key instrument in this kind of approach. So we will continue to extend and improve the multimodal visualization platform. That platform is super nice, and we will try now to come back to it when we finish this. If you have questions, we may want to go to the SYN tool or to the Arctic portal and try to explain or demonstrate or give you answers. Model fields and in situ data will have to be also more systematically made available on these visualization platforms. And a key message from us in the Synergy group is that we shall take advantage of some of these natural laboratories. The Agulhas, the Great Agulhas Current is one. The Gulf Stream is another. The Med Sea, we have them as well. We have a Lofoten Basin west of northern Norway. We have the Fram Strait here, etc., etc. If we could agree on having these as super sites that we would all like to sort of contribute to with whatever that could be of new observations in situ or a model, an experimental model or what, and gradually Fram Strait is sort of considering this area. Yeah.
You approach Svalbard.
We shall, yeah. But we have tried this before, and we seem to not succeed so well, although I must say that some of these strong areas like the Agulhas Current, ESA has decided to at least put that as a priority area for imaging mode SAR data. Sentinel-1 is taking data from that region on all flybys in extended wide or interferometric wide. So they do listen to us if we are having strong enough argument. It's also something of an interest that all of this frontal detection that we've talked about, why can't we start to get frontal detection being produced from numerical ocean models? This is something that would help us, and particularly if we are to sort of have a continuity of a frontal structure, let's say from optical data, which is suddenly being killed by clouds and there's no SAR coverage. What could we gain by combination of the model that has its frontal structure and the observational frontal structures? These things, we have to convince the modelers to start to produce these things out of the model. And another one is, of course, the model-based mixed layer. The sensor synergy is taking us a good way to advance the spatial temporal coverage for sure. And there's also a last point on this that I think Craig could be potentially interested in, and ESA, and that is that through sensor synergy, we could in fact emphasize the weakness in terms of space-time coverage, which in turn could be optimized through a orbit priority, an orbit selection, and a phasing. Rather than to start this from scratch and, well, we choose that inclination and we go for that repeat cycle. We could have something to tell you quantitatively from such a sensor synergy tailored to super sites. So I guess that's what we have combined, 60 slides. And we can take some questions and we can show you this portal eventually more to live it. That it's not just something we have on slides. It can be done in real time. So thank you very much. Eero, if I'm going to use this now to show, can we?
You need so plug in
This one.
Yeah. One of these Mac users.
Well, so that's okay.
Just that.
Yeah.
Well,
does.
See. Yep. Are you actually sharing something from there?
Should be.
Yep. Are you showing this mirrored screens or something?
No.
Do we have a Mac user here? We do. Come here, please.
So in the meantime, do we have any questions or comments? Yes, Kim.
Yeah, thank you. Just in line with your kind of last slide with your recommendations and future work, I was just wondering, could it be this both ways when you talk about the sensor synergy? That's also, for example, future missions from the ground observations. They could be also in correspondence with the ESA future missions as well. So that okay, you plan your future, I don't know, like a trip with a plane or with a vessel in the area, and exactly same time when ESA, because it's probably easier to coordinate something on the ground than changing the in space. So it's kind of both ways, not just one way.
No, I think that's a fair point. And indeed, I totally agree with you that if we had such super sites, it could be sometimes a reason to bring either some drone or some floating ships or whatever in there to do some specific data takes. Absolutely. Aha. Yeah, okay. No wonder. I need to upload this again. And then I have to do that. There you go. It doesn't move. So it's
it's frozen.
It's frozen. So I need to probably go out of it and connect again.
Just
You see, all of that is, so I do that. But then it seems to be, no, it's work. Why doesn't it work on, is it,
Been connecting that.
Jonny, vi har et online-spørsmål. Kan du argumentere noe mer om Mediterranean?
Om?
Hvorfor du skal ha en supersite i Mediterranean?
Oh, yes, that's a question. There was someone in the chat asking for what we meant with possibly a super site in the Mediterranean. Well, I would say that the Alborian Sea is one clear super site. It has all kind of very strong signals and some very persistent anticyclonic eddies just sitting there and making strong fronts. Internal waves is another reason. Then you have the Strait of Sicily, where there are also enormously strong dynamic structures. So there's plenty of areas in the Med Sea that could be interesting. So that could be the Italian gang and the Spanish gang that sort of is in charge of that. Then we have the high latitude Norwegians and the Swedes and the Finns and some others who are interested in the area of overwaters. We go for the Lofoten Basin, and then you have people for the Agulhas and for the Gulf Stream. And we have the same tools applied to all of these super sites. So we need to share tools, we need to share data, and we need to share our knowledge. It's easy to say, and it's not necessarily that difficult to implement. It just takes a will of some.
Just use your browser.
It's no internet. Let me just, oh, wait, let me see. I have to go in via this. And now, at least it's there. Okay. So what you see on this portal now is probably things you've never seen before. It's sea ice drift and upper ocean surface current. The white is the ocean current, and the red is the sea ice drift. The red is the sea ice drift from next sim model, and the white is the ocean, upper ocean, the surface layer current in the model from 2PASS, data assimilation system. So immediately you start to see things here that it's clear that the the ice drift doesn't follow the current. And it shouldn't, because the current has a source of momentum to move the sea ice. It's not as strong as the wind. So the sea ice would like to follow the strongest force, and that's the wind force. But then you could also argue that, okay, I should find a case now where there's no wind, then the sea ice should go with the surface current. Yes, maybe. But this platform is the high latitude Arctic portal of SynTool, and it's done in collaboration with Ocean Data Lab. And it has an ability to select dates on the lower path here, days, months, years, and one can have data being brought in from here, where you can explore satellite data, and you can start to find forecast fields for models. You can have in situ data, and so on and so forth. And
you were saying the sea ice should follow the wind.
Yeah, it's a good question. We were looking for that. It's not yet in, but we should have had ECMWF win. It's listed there, but it's still not, if you click on it, you don't get it. It's in the making, David. It's not there yet, but it is. Yes. But this is just illustrating this, perhaps for the high latitude as a super site. But the SynTool that is global can then be tailored to any region that you want to go for. So that's the case, and we invoke all the data. It's for the different applications and so on and so forth. So here you can, if we go back again, you can start to look at this, and then we can bring on the SAR data. Wasn't that? So it's wrong. It's the wrong. We don't keep them there for a long time yet. So here you see, just as an illustration, for this particular day in April, 5th of April, you see the SAR coverage, and then you can slide this time slice horizontally, so you jump from one day to the next, and you follow all the things there. And it is an illustration of the friendliness of the system and the opportunity to explore the synergy, and without having to sort of start a massive import of things from left, right, and center. And in the end, you just lose interest because it's so complicated. All of that is already done in the machinery behind here. So now it's you to use your eyes and your brain and start to explore this for your own interests and purposes. And I'm lecturing in satellite oceanography at University of Bergen Geophysical Institute, and the students are super happy with this kind of opportunity to see this into a larger context than just the retrieval algorithm for sea ice concentration from passive microwaves, or the CMOD wind retrieval model from AD. They like to see it in this kind of projection, and they're super happy with it. I think I shall stop because there is one last presentation this evening, or early evening, and that's Justin, who has he wants to bring to our attention an idea for a concept. Okay, you are there, so let us just make this into
Okay. Thank you.
And by the way, it's indeed synergy. This just for those who wonder what is to do with synergy. This is also synergy.
Okay, so the idea here is my colleagues and I have been looking at a lot of wave mode data. So these data, were designed for wave retrievals. But what's really interesting about the data is that it's global coverage and it's very high resolution. So you can see a lot of interesting features, and if you can map them appropriately, you can actually see nice regional structures. So we've been looking at these data for a long time. We maybe have gotten a little too far, so I really would like to get all the experts in the room to give their take on what the images are. So we made this little challenge here to do that. So maybe I'll just go one slide, be very brief here. Let's see if you're interested. Let's see.
It's the last one.
Okay. So this is little thumbnails of these wave mode images, and these are initials for all the different phenomenon that we see. So that's not novel by any means, and a lot of folks in this room have made better descriptions than this guide I put together here. But the idea here is to label these images. So the challenge that we have here is we pulled 50 random images from the globe. And the idea then is to label all the phenomenon you see in each image. And we estimate that this will take probably on the order of 30 minutes, I'd say. And if you're very fast, probably much faster than that. So if you're interested, you can email me and I can send you the directions, and I'll also send you this PowerPoint that I put together that gives you a quick guide on the different phenomenon here and what kind of textures you would see. Yes.
Your receival of your input.
Quality control. It's a little bulky with the system that we use, but I can give you some feedback on that. This is a competition, so sorry, a little late, I guess, for me. But the idea here is that you want to measure it accurately and as fast as you can. And then we have some ranking system to give out who would win. And you keep it anonymous. It's not to embarrass anybody or anything like that. We just want to make it fun. So you can, if you give me your email, when you email me, just give me the name or code that you want to go by, and we'll compile the results for the Friday dinner. And we'll give some prizes and try to make it fun. Well, I know, but no one else would know.